Recording is on.
Okay, great. So I can remove this as well. So German, thank you very much again. So yeah, so we had some problems with this in the main session, and we couldn't record it. So thank you for accepting to present it again. So it was very great.
No worries, my pleasure.
Thank you.
Okay,
Yes.
then let's dive in.
Yes.
So today I'll be talking about serving large-scale AI models, challenges and opportunities in the networking domain. Brief about me. So I got my Ph.D. from Politecnico di Torino in 2020. After that, I held numerous positions in Huawei Cloud between Paris and Munich, working mainly on data center networks and cloud networks. And since 2024, I'm a staff researcher at AMD in Singapore, working on networks and systems for AI. Before we dive into the technical aspects of the networking challenges, I would like to give you a little bit of context about where we stand right now in the field of AI. One key observation is that currently we have many different views and beliefs regarding the evolution of AI. Again, it's not a precise science, it's an empirical science. We have some scaling laws that tells us, oh, the bigger the model, the better it is. The bigger the data set, the more it can generalize. We have some fine-tuning evidence for improving the model accuracy. But again, everything is pretty much empirical. And there is currently a debate for what regards the next steps of the evolution of AI. So some people say that artificial general intelligence is achievable through more data, through increasing the model size, increasing the compute, and basically making models bigger, 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 and bigger. And this is what we observe right now. We observe that people are pumping data and compute into growing models. Again, this is, I like to say this fueled by the imagination of million people and the fear of being left behind in this race. We can see this as a new gold rush for this AGI. On the other side, you have people who are a little bit skeptical in the evolution of AI. They say that yes, AI is learning, it's able to reason. It is a form of intelligence, but it's not intelligence in the sense of artificial general intelligence. So they say, yes, we can increase the model size, we can increase the compute, we can increase the data sets, but there is a limit to what AI can achieve in its current form and its current state. On the other hand, you have people who say that ChatGPT is BS, and it's not me, but some researchers from University of Edinburgh. Again, wherever you stay on this kind of spectrum, you cannot deny that there is a heavy investment in AI. Investment in terms of manpower, investment in terms of infrastructure, like power grids, in terms of data centers, and again, from the governments, the investment in terms of money in order to try to stay ahead of other states in this race towards AGI. And we see this from the amount of innovation that we observed in the last years. So perceptrons are not new. They've been around for quite some time, since 1960s. But they really didn't become popular up until 2012, mainly due to the limitation in terms of compute and data. So the architecture didn't change that much, but what really changed is the available compute and available data sets that we have. In 2012, we first saw a deep neural network. It was AlexNet, outperforming traditional algorithms for image recognition. And since then, we had a lot of research going on in trying to apply DNNs for different domains, mainly for, again, pattern recognition and optimization problems, up until 2018, in which we got the first transformers. Since then, I would say nothing too exciting happened up until one day in which we woke up in 2022 with the release of ChatGPT, which became the most popular product and the most rapidly growing product ever. Since then, it's been a roller coaster of emotions with different techniques for improving the accuracy of these LLMs. We had a mixture of experts, agentic AI, multimodal models, reasoning models, and this slide is already outdated, even if it's just 6 months old. I mean, it is a roller coaster of emotions, and it's quite difficult to stay on track of what's going on in the field right now, because everybody is throwing manpower and money in this domain. So every day we wake up with like 20 plus new papers to read, which is, I would say, a little bit overwhelming. But regardless of this kind of innovations, MOEs, agentic AI, reasoning models, as I was mentioning before, the main innovation that drives the accuracy of these models is the model size. So we went, I was mentioning before, from 1960s with very small perceptrons, which were able to do some basic logic. And back at the time, we had like hundreds of perceptrons, up until today, in which we have this explosion in the number of parameters within a single model. We get to, again, this slide is a little bit updated now. I think we push the boundaries even higher on this chart, but now we have a 10 to the power of 12, or up until some months ago, we had 10 to the power of 12 parameters in the frontier models. How this can grow in the future, this is still to be seen. But one thing which is undeniable is that to support these kind of big models, the traditional accelerators, traditional single GPUs are not enough anymore, because you cannot basically fit these such big models within a single GPU. And this was what we observed. From 2016, we had Radeon Instinct MI25. Saying 25 puts a smile on my face, because currently we are developing MI450. So it's been quite some generations between this and the recent GPUs from AMD. And what we had for this kind of GPUs, in terms of compute, we had 5.7 teraflops of FP16 precision compute, 16 gigs of HBM memory at 224 gigabytes per second, modest 300 watts of power requirement. And again, now I say laughable, but back at the time it was quite an achievement, 100 gigabits per second of networking. Fast forward 10 years, models grew up by many folds. What we have right now is this kind of beast, which is AMD Helios platform, that is able to achieve 500 times more compute, more than 2,000 times memory in terms of the amount of available memory, but at the same time we went up to 8 terabytes of terabytes per second of the throughput for the memory. Additionally, one critical thing is the energy consumption of this kind of beast is 600 times more than the previous example that I mentioned. And most importantly is the networking stack. We went from 100 gigabits per second up to 30 terabytes per second for networking. And why we do this? Well, again, to support larger models. So, of course, you cannot put a single model into this kind of beast. What you need to do is to split the model across multiple GPUs or multiple blades within the model. And this is a simple example of how you do this. You get a very big model. Suppose you get like the latest Llama model, and you partition it according to some parallelism. Can be tensor parallelism, can be pipeline parallelism, expert parallelism, you name it. You partition it across different compute nodes. And what you do to restore the natural data flow is to introduce some communication between these compute nodes. And you can see that whenever process 1 finishes computing something, it sends the output to process 2, then to process 3, process 4, and so on and so forth. This communication pattern can be different, but what is important to notice is that these communication patterns are pretty regular. So this is an example of a traffic matrix between different processes or ranks in this case. You see that the communication pattern is pretty much regular, which means that from the networking point of view, it's not that challenging, let's say. I will get into details of whether it's still true or whether it is actually challenging or not. But I was mentioning that whenever there is a compute at process 1, it follows some communication phase. So let's see what happens at the compute communication ground. So we have an example of how compute and communication runs at a single rank. So whenever you finish doing some compute, whether it is some FFL layer, whether it is an attention layer, it can be anything. What you must do after this is to perform some communication with some other ranks. And this communication can be or reduce, scatter, whatever, depending on the kind of parallelism that you use. The problem with this is that, as you can see, is that you may end up in situations in which you have idle compute. And idle compute in this domain means wasted money, wasted revenue, or wasted power. Again, this kind of idle compute will hurt both the performance because you're shrinking, you're wasting some CPU cycles or GPU cycles in this case, but also in terms of revenue because you're not able to serve any, for example, user requests if you're running ChatGPT in this kind of time. And this repeats over time whenever you need to perform some communication. So the idea is, can we reduce this exposed communication? Simple intuition is yes. Let's reduce the amount of communication that we do. So how can we do this? Multiple ways. I would say simplest way is to throw more bandwidth at the problem. So in this case, suppose you have 100 gig link. It takes T amount of time to perform this communication. Let's add another link. So we double the bandwidth on our links, and consequently reduce the amount of exposed exposed communication in this case. And again, we reduce the amount of wasted compute as in this scenario. But the problem is that we are still waiting for the network to transmit something. You can throw as much bandwidth as you want at this problem. As soon as you jump to a next generation of GPUs, which is more performant, which is faster, you still end up in a situation in which you have exposed communication, and in the end, you end up in this scenario in which the compute is still blocked by the networking, and you still need to wait for the communication to finish before you can start doing the next computation. Additionally, just throwing bandwidth at the problem is not the right approach because of power budget within the compute racks. Nowadays, these compute racks, like the one that was showing you before, the Helios rack from AMD, is mainly bottlenecked not by network, not by compute, but by the power density. There is this amount of power you can feed without a rack before it catches fire. The limitation, the main bottleneck of this is cooling and heat dissipation. And let's look at this graph to see what's going on if we just blindly throw bandwidth at the problem. So I have 3 bars here, which represent 3 different generations of GPUs with 3 different speeds for the access links. This is the generation we're currently in, and you see that most of the power is drained by the GPU. The networking, which is the green and the light blue, contributes a modest amount to the total power drained, and this is the current state-of-the-art behavior of current GPUs. As we keep increasing the generation of our GPUs, what we observe is that we keep doubling the link speeds, and surprisingly, what happens is that the power of the GPU doesn't grow that much relative to the power consumed by the networking stack. So in this case, these 2 bars, the light blue and green, which is the core components of the networking stack, contribute up to 38% of the total power budget, which means that we're getting closer to the total power consumed by the compute, which actually gives revenue to the customers, as opposed to network, which is there just to support the compute. So this picture tells you, like, okay, we cannot just throw bandwidth at the problem. So in the following, I'm going to talk about some approaches that we can use to reduce this exposed communication and try to speed up the communication without actually increasing the bandwidth on the physical links. Before getting into that, I would like to present some power saving opportunities in this domain. So if you remember, I was showing you this figure that was showing how the compute is periodic, and you have gaps in the compute, but you also have the same gaps in the communication. So you have some time in which links are basically idle. So the links are waiting for the compute to finish before they can start transmit data. And the intuitive question is, why don't exploit this link idle times? So why not using this link idle times to try to save some power on the networking side of the system? And this is what we did in one of our work. What we propose to do is to just turn off the interface. So whenever a communication is not ready, so in this case is this blue rectangle, what we do for the interface, we just switch it off. And this allows you to save some power. If you look at the previous picture, especially for 3rd generation of GPUs, in which the network contributes to almost 40% of the total power budget, this, in theory, allows you to save quite some power that can be redistributed to some other task, like redistributed to compute or to cooling, or you name it. And we showed that it works pretty well. So we gathered some traces, we ran some training jobs on MI300 GPUs, and we actually showed that it's quite beneficial in its naive case, in which you just turn on the interface whenever a communication is ready. So in this case, communication at rank 0 is ready at this time, and at this time you turn on the interface. But the problem is that these ranks, they can have some skew between each other. So some of the ranks can be a little bit slower than the other ones. That can be due to manufacturing defects, or due to the improper cooling, or due to physical location of these racks. And if you look at GPU2, at rank 2, this rank is running a little bit slow compared to the previous ranks. So it is ready a little bit later as opposed to the other ranks. So what we propose to do is to, instead of turning on the interface as soon as a given rank is ready, we turn on the interfaces when the slowest rank among all of the ranks is ready. In this case, rank GPU2. So even if GPU 0 is ready in this case, at this point, we still keep the interface off because it doesn't make sense to turn it on unless all of the ranks are ready. And we obtained some very interesting results for different models. We'll not go into details, but for distributed data parallel, you can save 90% of the total power budget dedicated to networking. For some other models, like the Slama 370B, the gain is a little bit modest, in the range of 20%, but still this gain comes for free without penalty for the model execution. For some other models like this DeepSeek, it's somewhere around 50%. And we show that our approach, which is the orange bar, outperforms the naive approach, which is the one on the top right, by up to 20% in some scenarios, and it's not that far away from the optimal, the Oracle scenario, which is this green bar. So this is nice. This allows you to save some power, but the question now is, can we do even better? So if you want to do even better, you need to shrink this communication in order to increase the link idle times. How to shrink this communication without increasing the bandwidth? Let's dive into compression techniques for communication. So we worked on this for, I think, close to 2 years. And the idea here is that, okay, you have to transmit some data, but what if this data contains a lot of redundant bits? So look at this bit stream that you have to transmit over the network. Most of these bits are 0. So it doesn't make sense to transmit it if you have a good enough compression techniques that can compress this data on the fly and only transmit the actual useful and meaningful data. And this is what we try to implement. The idea is very simple. Again, you have 3 ranks here, GPU 1, 2, and 3. And whenever application performs some computation, what you do is to transmit only the blocks of data that are non-zero. So this is a very simple compression technique. But even under such a simple approach, what we show is that we can gain quite some effective bandwidth or goodbut as compared to the baseline. So in this case, the baseline is the dotted line, and we are comparing different collectives with different amount of sparsity. Sparsity is the degree of zeros in a given block of data. And what we can see is that for very sparse data, like 90% in this case, you can achieve an effective goodbut, which is higher than the link bandwidth. So basically, the compression allows you to transmit more useful data than the link allows you to do, which is impressive because in this case, you are basically doubling the effective link bandwidth without actually adding extra links to the network, to the system. And what is the outcome of this on the model performance? So we showed that for Llama 3, for the training jobs of Llama 3, 70B, if I remember correctly, we observe a 15% reduction in the total execution time because you shrink the exposed communication, so your GPU is more your GPU compute is more loaded. As you can see here, the compute increases, the communication decreases, and the exposed communication is half of what we would get without the compression technique. And the impact, so all of this compression is done in software, and the impact on the actual compute load is pretty much negligible. So far, I was talking about. I was mentioning at the beginning of the presentation that that from the network point of view, these kind of workloads are not very challenging, because if you remember, I was showing you this traffic matrix, which was very regular. There was no congestion. Every rank was sending to the next rank in a ring fashion, or according to some very regular communication pattern. The thing is that this was true up until maybe 1 year ago. Now things start to change a little bit. And let me tell you why. What is the main culprit in making these communication patterns more difficult to manage nowadays? So the main culprit is asymmetric collectives. So before, my collective was a symmetric ring. Now this ring is not that symmetric anymore. Let's see why. One of the biggest innovations in the last year in the field of AI and model architectures was the introduction of mixture of experts. Let's see how it works in practice. So the traditional transformer layer is composed by attention block and feed-forward network. This feed-forward network is a big matrix multiplication. It's the huge matrix multiplication that takes most amount of time, most amount of compute, and most amount of energy in your transformer block. The key intuition of mixture of experts is to take this huge matrix multiplication and split it into multiple small feed-forward networks. So in this case, this huge matrix multiplication is split into m smaller matrices, matrix multiplications. All of them are feed-forward networks, and all of them are trained to be specialized in some particular task. So all of them are trained to process specific tokens of your input request. And in this case, the new transformer architecture still includes the attention layer, but it includes this additional block, which is called router. And this router is also a small FFN that decides where to send your tokens. Simple toy example, it looks at the token and says, oh yeah, this token has something to do with some coding question. So the user is asking me to write a script. I know that expert 1 and expert J are specialized in coding. So it's going to forward those tokens to expert Y and expert J, which is okay, which is good. But then the problem is that, so the advantage of this is that you reduce the amount of compute, because for every token, instead of activating this huge feed-forward network, you only activate a small subset of these feed-forward networks. From the compute point of view, is amazing. From the networking point of view, it's awful, because if we look at the traffic matrix, at the new traffic matrix, in which you have the again the ranks, you can see them as ranks, source ranks and destination ranks. You see that now the traffic matrix is very skewed. You have most of the traffic going to only a handful of ranks that host the most popular experts. Which means from the network point of view is that you have congestion. You have problems with load balancing. You have incast problems. All of the old problems that we used to see in the traditional data center networks are coming back. How to solve this? We have worked on this again for like, I think 2 years, more or less. And we come up with two different approaches of how to solve this, what we call imbalance. And first imbalance that we address is expert imbalance. So I was mentioning before that within a single GPU, some of the experts may be more popular. And in this toy example, you have GPU 0 holding 4 experts and GPU n holding the other 4 experts. And the experts in GPU 0 are more popular, which are these red experts. They are activated more, they receive more tokens to process. While GPU n is not that loaded, so it observes a load of 0.6 as opposed to 1.5. And it hosts 3 experts which are not that loaded as opposed to GPU 0. Key intuition here is, okay, let's rebalance the experts across these GPUs. And this is what we did. So, let's look at all of these experts and get, for example, expert 2. And from GPU 0, we put it in GPU n. And from GPU n, we get expert j plus 1, and we put it in GPU 0. The resulting load, total load on the GPU, on the GPUs is 0.9 and 0.8. So the difference between the loads is minimized. And by minimizing the difference between the loads, what you do is to minimize the response time of your requests. Nice. I mean, now we reintroduce load balance across the GPUs. Consequently, the load imbalance on the network side is also minimized because now the traffic matrices are more uniform. But the problem is that you need to be very careful how to rebalance. So existing algorithms, the way existing algorithms work is that they take all of the experts, they look at it, do some naive optimization problem, like set partitioning problem, and in the worst case, they shuffle all of the experts across all of the GPUs. When you shuffle these experts, what happens is that from the practical point of view, you have to load new experts from the memory or load new experts from other GPUs and unload previous experts, which means that you have to pay in terms of time to load and unload these experts. And you see, if you shuffle all of the experts, you're basically falling in the worst case in which you have to load and unload all of the experts. So you're paying the maximum penalty to rebalance your experts. Our intuition is that, yeah, you don't really have to do this. What you need to do, instead of blindly shuffling the experts, you move the experts in such a way to minimize the total overhead of serving your model. And in this case, the total overhead is the load balancing overhead, the resulting MOE compute, which depends on the load imbalance across all of your GPUs, and the MOE communication, which again is, we can say is proportional to the load imbalance across the GPUs. So we implemented this as an ILP optimization problem. We have some heuristics. We have done a lot of experiments. Let's look at the results. We compare the baseline EPLB, which is naive shuffling algorithm, our heuristic, and our ILP, which is the optimal in terms of latency. What we see is that all 3 algorithms can achieve a better balance. So here 1 means that every GPU has the same load. 0 means that 1 GPU has all load and all of the other GPUs have 0 load, basically. So it's just a metric of showing what is the most loaded GPU normalized to the load of the other GPUs. You see that all of them are pretty much close to 1, which is fantastic. Again, mean normalized standard deviation, similar metric. 0 is better, 1 is worse. All of them are very close to 0. But when it comes to, let's keep algorithm runtime, when it comes to the number of experts that we move, the naive approach moves 13,000 experts. This is for DeepSeek V3. Our algorithm moves 5 times less experts, which means that the time overhead of rebalancing, of moving data around, is 5 times less. Additionally, a positive thing is our heuristic is able to outperform EPLB in terms of runtime, which is nice, even with a naive implementation. Again, this number can be further optimized, but we're not that interested in optimizing this as opposed to optimizing the overhead. So let's hear the results. What are the total? What is the impact of using this kind of latency optimal expert load balancing? So algorithm runtime, I think it's already shown here in the table. Let's look at the rebalancing latency, which is directly proportional to the number of experts that we move. Well, we observe less than half total rebalancing latency. Why it's not 5 times less? Because you have some other overheads when you need to move data around. So it's not really like one-to-one comparison. You have overheads with kernel launch times. You have overheads with issuing reads and writes from the RAM to the HBM. You have some networking effects here. We have a lot of stuff going on here. But the interesting thing is that this latency here, the rebalancing latency, is the one that dominates the total latency of performing the rebalancing across the GPUs, which is nice. It's the point that we wanted to prove, and this is what we proved. What is the advantage of this? Well, the advantage now is that not only you can rebalance more rapidly, but you can also rebalance more frequently. So in the case of inference workloads in which you cannot predict the token distribution in advance as for the training jobs in which you have the data set, and you know the data set is going to be like this for the rest of the training. In the case of inference, this allows you to rebalance more frequently and allows you to achieve better overall response time for your users. Nice. Let's see at a different technique. So I was telling you that with this kind of approach, we can rebalance more frequently for inference tasks. But on the micro level, you still have some imbalance between different requests, because you may have for example, you may have interleaving of requests requiring coding and requests requiring summarization, which require different experts, which means that on the micro level, you still see a highly skewed traffic towards some experts or some other experts. What can we do to solve this issue from at the network domain without rebalancing the experts? Because in this case, we cannot rebalance the experts at every single request. Let's look at this toy example. So this toy example shows your data center fabric, and you have two requests for some experts coming at input port 1 and 2. So in this case, this single request requires 4 amount of tokens from output port 1, 3 amounts of tokens port number 2, and 1 amount of tokens at port number 3. Same thing for the green requests, and the total response times of this request depends on the slowest processing time, and the same again for the green requests. What happens in the network when it receives this data? Well, the network is not aware of what's going on inside these flows. The network just sees flows, and the way that the networks are designed is to perform some fair share across all of these flows. What we see is that at output port 1, when you have export 1, you have a fair share between this big flow and this big flow. Same thing happens at output port 2, in which you have a fair share between this flow of size 3 and this flow of size 2, and the same thing happens at the output port 3. If we look at the total completion time of the blue request and of the green request, we see, as I was mentioning before, it depends on the slowest flow across all of these three. In this case, the slowest flows are at port 1. So in this case, the total completion time of the request, of the blue request, is going to be 4. Even if here it finishes a bit earlier, it's still going to be 4 because we need to wait for the slowest flow. And the same is going to happen for the green request. Again, it's 4 in this case. The average request completion time in this case is going to be 4 plus 4 divided by 2, 4. Can we do better? Well, the answer is yes. If we implement a co-flow, a collective aware scheduler. In this case, the scheduler is aware of what's going on at port number 1, port number 2, and port number 3. And what it does is to perform some unfair scheduling of the flows in such a way to minimize the total request completion time, as opposed to guarantee per flow fairness. And if we look at this example here, in this example here, the blue request finishes at time 2. So actually, all of the flows of the blue request finish at time 2, and the green request finishes at time 4, as in previous case. So the green request is not penalized in any way by this unfair scheduling. What happens is that the average request completion time in this case goes from 4 to 3, because we have the blue one finishing at time 2, the green one finishing at time 4. 2 plus 4 divided by 2 is 3. Nice. So it means that if we map these to the MOEs, which exhibit exactly the same behavior, in which you have flows of different size going to different experts, we can implement some MOE-aware scheduling, and this is what we did. So what we showed is that if we look at the green bars, which shows you the normalized latency, average latency of completing the request towards, of completing the entire request for a subset of MOEs, we see that if we apply this collective aware scheduling, we can reduce the request in some cases by the request completion time by up to 30%, without introducing any significant amount of complexity in the network. An interesting result is that you don't have to do it for every single flow within a request. What we show is that it's just enough to take the biggest flows within the requests, and this is given by these numbers here. 0.2 means that we only apply this policy to the 20% of remaining flows, and 0.8 means that we apply it to 80% of the flows. What it shows you is that even if you just apply it to 20% of the biggest flows, the policy still performs very well when compared to the Oracle policy that applies this scheduling at a very fine-grained level to every single flow, which makes sense because 20% of the flows are the longest flows, which block the entire request. In this case, it's these 2-4 sized flows, and it's just enough to optimize these two in order to bring significant benefit in terms of average request completion time. Amazing. So I've been talking a lot about optimizing this, optimizing that, optimizing energy, optimizing providing data compression, using advanced flow scheduling. And so far, all of the techniques that we talked about are implemented either in software or on the GPU level at the kernel level, which is, again, software level. What we observe right now is that there is not a significant overhead, but there is still overhead of doing this in software. And additionally, what we observe is that there is an increasing body of work that targets network offloading for some of the tasks. In this case, you have some of the papers that do some finance applications like limit order books. On the SmartNIC, we have some reinforcement learning for congestion control. Again, that can be done at the SmartNIC to reduce the overhead, to reduce the latency. Some smart load balancing for, again, networking, traffic scheduling and optimization related to the previous work that I was talking about, and our work for MOE load balancing. All of these kind of applications map quite nicely to SmartNICs and to network devices like smart switches. So what we've been working on in AMD for, again, past 2 years is to provide an infrastructure for implementing all of these approaches and all of the approaches that I mentioned before on top of SmartNICs to make the systems more reactive, to reduce the compute overhead and reduce the total latency of running these algorithms. And we come up with this P4 AI framework, which I think is super cool. What it does is to combine some FFNs or some CNNs or some neural networks tailored for example, one of these applications with easy to program interface for packet processing, in this case, P4. The magic of this is that you import your neural network, you expose it to P4 like as an extern, and what you do is to feed packet or flow features that you can, as you may know, you can easily extract through the P4 pipeline. You feed them through the FFN on the fly at line rate, and you use the output of the FFN directly in P4 to perform some packet processing. For example, load balancing, congestion control, scheduling of that particular packet, or compression of the packet, as I was mentioning at the beginning of the presentation. And the magic of this is that you write everything in a very user-friendly way, and what it does is to generate RTL code that you can deploy directly on an AMD FPGA SmartNIC. And this, I think, is an amazing project. I invite you to check it out. It's open source. We open sourced it quite recently. If you have any feedback or you want to try or you have any issues, write to me and I will connect you to the colleague who developed this framework. And with this, I come to the end of my presentation. Let's go quickly to the conclusion and of what we talked about in this presentation. So I think the main point is that network bandwidth scaling is reaching its limits due to the manufacturing limitations, due to the power constraints, you name it. The problem with this is that we need to find other ways of increasing the efficiency of our networks, and I introduced some of the examples like compression, rebalancing, and exploiting link idle times to reduce power consumption. Again, I think I talk a lot about power. it started to become a bottleneck in large AI clusters. There is this much power you can compress within a single rack, and there is nothing we can do about this for now. Sparsity-aware flow compression is one of the techniques that we can use to approach these issues, to provide higher effective good food, which apparently exceeds the link rate that is available in our clusters. Finally, mixture of experts are here to stay, and I show you they introduce a lot of headache from the system and network points of view in terms of imbalance in the compute and the network layer. And this requires careful attention for optimization. Future directions, power. Again, we talk about power management, not only the network layer, but also at the compute layer. We had some work from our colleagues from the US team working on dynamic power management, which is based on the workload that you receive. So this requires a lot of investigation. It's a very hot topic. I would kindly invite anybody interested in AI clusters to focus on this topic, which is not a sexy topic because it's not networking, it's not compute, it's like power. Not a lot of people work on this. It's highly relevant for the industry. Congestion control and flow scheduling is starting to become, again, first-class citizen in AI data centers. As I showed you before, it's not sufficient to just throw bandwidth at the clusters. You need to bring back congestion control and flow scheduling and load balancing. All of the old problems that people worked on for 20 plus years are coming back. System level algorithmic optimization. So I didn't talk about this in this presentation due to the time constraint, but inference is the biggest topic right now. So we go from training, which was, I would say, easy from the system point of view, so inference, which is highly dynamic, highly unpredictable. And this creates numerous challenges for cluster orchestration, network orchestration, and the development of new frameworks for serving these big inference models. Heterogeneous inference clusters. This, again, huge topic. Nowadays, you have new GPUs being released every year. What you do with the old GPUs that you pay hundreds of thousands of dollars, well, you cannot throw them away. So you need to find a way to efficiently use those old GPUs or previous generation GPUs in a cost-effective way. Again, power comes into play here. Orchestration comes into play here. Very hot topic. Highly recommend to work on this. Finally, and I conclude here, in network AI, people have been talking. When I first started my PhD 10 years ago, people have been talking about, oh yeah, we put AI into P4 switches. We deploy simple FFN, simple CNNs on the PISA pipeline. Idea is nice. What are the use cases? I think the field is quite mature right now in terms of technology. As I showed you earlier with P4 AI, need more use cases. So we need to come up with good enough use cases to make this in-network AI a first-class citizen in the future of networking. Thank you very much. With this, I conclude. You have some references here if you want to have a look at the presentations, at the graphs and data that I showed here. And thank you for your attention.
Yeah, thank you very much, German. It was very, very, very interesting to talk and presentation. And
thank you for inviting me, Masoud.
Thank you very much actually for letting us and having you. I don't know. Is it? I have some very quick questions, if it's okay. About this, the framework that you mentioned for like having
Yes.
the. This is. I mean, how is the process? I mean, this is like because I have. I see some other platform like Planter that is basically
Mhm,
developed by the same group of the Noah Silverman. For
mhm,
that framework, we pass the network to their framework, and their framework generate the P4, and then with this
mhm.
P4 we can program the device. So is it the same
Yeah.
process for this P4 AI, or is it different?
Um, so like for before AI, I don't know if I have a backup slide here. Let me see. I don't. I don't have a backup slide here. But we use a set of optimization techniques. So we use model quantization and additional optimization techniques in order to be able to fit big enough
Mhm.
CNNs on a single GPU while still guaranteeing line rate. Because the problem with this approach is that you need really a lot of model optimization and a good enough compiler to satisfy timing requirements to be able to process at the line rate. This is the biggest part. Um, and for this, we use additional software from AMD, from Xilinx,
Okay,
which
yeah.
again part of AMD right now
So
that
it
is able
needs
to guarantee this. Yeah,
so it needs extra. And then
yeah.
my another question is that for this load balancing between the experts
Mhm,
in the GPUs,
mhm.
I mean, how do you, what is the protocol for like communicating between the GPUs? Is it a GPU direct or something, or no? It's not?
Depends on the kind of architecture that you have. So in this case, the way that we develop the entire optimization mechanism is that it's agnostic to the kind of interconnect you have. What you give him, what you give it the some generic network topology with link speeds and latencies, and it computes like optimizes everything. In practice, within a single node, you're going to be using Infinity Fabric if you're using AMD, NVLink if you're using NVIDIA. And in some cases, instead of doing inter-GPU communication, what you may want to do is to just load these weights from RAM. Because these models are available at every single GPU. All of the experts are there. What you need to do is to load it from the PCIe Express bus, basically.
Okay, okay.
It all depends, and this you can model it. Again, the PCIe is a link, so you can model it as a link in your network, and the optimization algorithm can decide where to fetch these experts from. So I think it's a very interesting problem to be solved because it also connects with the topic about heterogeneous interconnects and heterogeneous devices. Again, it's not only the devices, also the network is going to be heterogeneous. So I think very interesting field to
Yeah,
explore.
yes,
Yeah.
exactly. Yeah, it's very interesting. Yes. So thank you very much, and actually, thank you. I really appreciate it that we have one more session to record it, because it was very pity that if we don't have it, so
Yeah,
everyone
definitely.
can use it. Yeah. So then I can stop sharing